Okay, I'd like to welcome Jason Barra as our speaker today. Jason received a bachelor's in chemical engineering from Virginia Commonwealth University and PhD in chemical engineering from the University of Colorado at Boulder. He's a well-published author and on topics such as CO2 capture, ionic liquids, polymer membranes, nanostructured materials, and chemical process engineering. And Jason's also the 2015 winner of the AICHE FRI John G. Knoosh Award from the Separations Division. And he has many active, an active research group. But today he's going to be talking to us today about Chemical Engineering AppSuite and ODEsseus, a numerical solver for differential equations on iPhones and iPads. And one of the things that we're especially excited about with this presentation is, opening up these apps for chemical engineering education and also for chemical engineers, as using apps increasingly is becoming more important in everything we do. And so Jason's going to give us an overview of some of his work that he's done in this area, and hopefully it will lead to a great discussion on this topic. So Jason, I'll go ahead and turn the presentation over to you.
Okay, great. Thanks, John. I appreciate the introduction. I appreciate the opportunity to do this today. This is a topic I've been really excited about for a few years now. It goes back to when I started teaching really in 2011. And yeah, the title of my talk is Mobile Apps for Chemical Engineering Education, specifically the ones that I've been responsible for developing here with a couple of colleagues at the University of Alabama, or former students at least. So I'll acknowledge them first. My main collaborator on this has been J.P. McLemore, master's student, graduated in 2012, but actually was the guy that taught me how to code for Apple machines. He's currently with Schlumberger, but the beauty of working on software is we can do this remotely and collaborate. I knew we'd catch up every couple months or so, but him being in Scotland and me being here is really not a problem when it comes to collaborating on software. David Ravita has also helped out with some of the code. A lot of his work hasn't made it into the app yet. He's recently graduated and currently in medical school, so I don't see him having much time to put into the app anymore, but he's made some nice contributions. Also the computer-based honors program, which was David's sponsor for this over a couple of years. And then Professor Heath Turner, who's just been a big advocate, resource for coding knowledge, has really helped get this along, helped me write a few proposals on the app as well. So with that, I'd like to start the discussion on just thinking about a Crossroads and how we work and teach. Now, I started chemical engineering 1998, 1999. Really, I took math and energy balances, and this was what I had to bring to class every day. We used Felder and Rousseau, but I put the Himmelblau book out there as well because I think it's going to be relevant here in a moment with something I'm going to show. But we had calculators, pens, paper. I had a unit conversion card there that my professor, Dr. Gary Huvard, made for everyone. We had a laminated unit conversion card that we carried around. And of course, we had laptops or desktops or whatever. And now the question becomes, 15, 16 years later, can we do the same thing or can we do more with less? And I use my desk there being cluttered versus being very organized as a contrast. Can I do a lot of these things that I traditionally did on pen, paper, textbook, on an iPad? And maybe, maybe not, maybe it's a mix, but it's certainly worth exploring. So in going back, when I started looking through apps and things that have been done in the past, it turns out that Himmelblau and a lot of these textbooks, they had the concept of an app a long time ago, except the app was frozen on a CD-ROM, and we had to go and put the CD or install the software on our desktop and laptop. So it wasn't as convenient as a phone, but the concept of having a module where I could put in a molecular formula or I could pull up a compound name, get some properties, do some calculations very quickly with my computer rather than integrate a heat capacity by hand, for example, or do double interpolations in a steam table. This was recognized a long time ago that computers can really help us do this. But with these CD-ROMs or some web modules, I like to think about that the activation energy to get this information was fairly high. I had to sit down in front of a machine somewhere and pull this up. I couldn't just reach into my pocket and get this information. So again, the concept of an app has been around for a while, but the beauty now is when we have smartphones and tablets that this is in our pockets or in our backpacks or whatever at any given moment. So the activation energy gets quite a bit lower. I also like to think that with the modern tools and frameworks that Apple and other software platforms provide us, that there's a lot more we can do that just wasn't possible with these older, what I call apps. So again, my motivation, where did this come from? I started at the University of Alabama in 2010 in the fall. I got a semester off from teaching. And then my first semester was spring 2011, and they threw me right into mass and energy balances when I started. And I taught that class for 6 semesters. And then I've moved on. I've been teaching separations for 4 semesters, but those 2 classes have a lot in common. There's a lot of need to do mass and energy balances, obviously in both. We have thermodynamic properties, physical properties, steam tables, vapor-liquid equilibrium, Raoult's law, all of these things mesh. So for me, teaching those 2 classes, as well as the needing to teach the thermo that goes with it, this is actually a great framework to which to develop apps around. So when I started teaching in spring 2011, it was also about the same time I started getting into iPhones and iPads and all that good stuff. I just hadn't been as active in technology or, mobile devices just yet, but I started getting into that about that time. And so I said, wouldn't it be nice to have, apps that we could put on our iPods or iPhones? And I went and I looked in the App Store, and there's really still truly a lack of functional apps dedicated to chemical engineering. Now there's dozens, if not hundreds, of unit converter apps out there, and that's great. That helps us a little bit. There's a few steam table apps out there as well. But for the most part, those apps that claim to be for chemi or specialized engineering, they don't have a lot of features. Some of them were quite poor. Maybe some of those have disappeared over time. But nonetheless, there wasn't enough out there to satisfy what I had a vision for and how I wanted to use apps in teaching. I also started to notice that in my first semester or 2, I was still solving routine equations by hand, still doing the integrations of heat capacities, just all kinds of things that took time away from instruction. Even solving the ideal gas law takes a few moments, and forbid that we have to do Peng-Robinson or some of these other equations of state in the mass energy balances course. This consumes time, right? Not only do I have to look up values or constants in a table, I then have to calculate other constants from those constants. I've got to do linear or double interpolations. I've got to do graphing, right? And I wanted to do this all instantly, right? I wanted to save time in my instruction, as well as help the students. Again, once they appreciate how to do a calculation, do they have to do it over and over again the same way? So I put it on myself, and I asked my class, I said, who wants to help me write an app? Clearly, no one else is going to do this unless we take the lead, right? So that's how it got started. And, of course, working on a platform like iPhones and iPads, we also need to make it really nice, right? I mean, that's one of the things I think that gets overlooked a lot of times in engineering is function over form. I wanted to have form and function. So not only make it powerful and useful, but also make it nice and fun to work with. So for my vision for where I want to go with apps and chemical engineering, again, it comes back to putting powerful and real-world problem-solving tools in students and professors and professionals' pockets, right? It's this inertia that it takes to get into learning or work mode. And I think the students, again, they're so used to turning on and off at discrete times. Class starts, I'm learning. Class ends, I'm done. Maybe I'll pick it up again when I go to do homework. But if this is in my pocket and it's next to Facebook or Instagram or Twitter or whatever other apps I've got on my phone, then again, chemical engineering and learning becomes just the same as clicking on social media. I also see the benefit of having these apps, and it's helped me quite a bit in designing homework and exam problems. I'm no longer trying to determine whether or not that equation of state I'm using, if I'm calculating it properly, or if I've got a feasible answer. It also expedites my grading. I know what the answer is going to be without having to solve it for myself all the time. And again, I want this to be something students will continue to use after they graduate in an industry, right? So not just something that's as soon as they graduate, it's no longer useful to them. This is the kind of stuff that I want them to keep using as they go into their jobs. Also, I see a real need in chemical engineering for on-demand practice and homework problems. Again, with solutions manuals being posted ubiquitously online, especially courses like Felder and Rousseau, the solutions manual for the 3rd edition. Every student has it probably on the first day of class. So it makes the homework problem somewhat difficult to manage when all the students have the solutions manual at hand. So Sapling Learning is a company I've worked with for a few years to offer an alternative mass and energy balance homework sets. They do a great job. But again, I think there's still a need for more problems, more courses, and deeper randomization and diversity of these problems. Because again, it's only a matter of time before clever students can break this and write their own solutions manual to something like Sapling. And again, I think the other thing that's been missing historically is a parametric analysis of outcomes. We need more what if this changes rather than the one and done answers. If I'm running a mass and energy balance, oftentimes I just have the students stop and say, well, solve for this variable. But I like to think that if we think about what if I change this variable, how does that propagate throughout the process? You know, this can be more powerful. So I'd like to build that into our practice and homework problems. And finally, make this accessible to anyone, right? If I'm selling apps on the App Store, anyone in the world can buy this, whether they're a Chemi student, Chemi graduate, or just interested in this at all. So I think that's one of the interesting and powerful features of this ecosystem that Apple offers, is that it's accessible to anyone. Okay, so why Apple? Briefly, you know, I always get asked, why don't you have Android apps? And I said, well, we're 2 guys coding. We only have so many resources. And again, we got to start somewhere, right? So if I spend all my time trying to write Apple and Android apps, then I'm probably not going to get as much done as if I just stick to one platform. Also, at the University of Alabama, there's been a strong preference for Apple products. We have an Apple store on campus, which probably contributes to some of that. But when I surveyed my class recently, I saw that of those owning smartphones, which was almost the entire class at this point, more than 75% of those were iPhones. And those owning tablets, not e-readers, things like Kindles, which was a little more than 1/3 of the class, almost all of those were iPads, right? So when I took it all, accounted for everything, at least 90% of the class had access to some iOS platform in one form or another. So I said, well, that's certainly justification to keep working exclusively on Apple. Now, would we love to do other platforms? Sure, we just don't have the resources just yet to do that. Plus, again, Apple is tailored to my own personal preferences when it comes to devices and my strengths in writing code myself. So after about a 8-month development period between the time I started finishing teaching my first semester of mass and energy balances, that was about May 2011. January 2012, we released our first app, which was Chemical Engineering AppSuite, which was designed for the iPhone and iPod Touch. We're currently on version 3, which was the last updated in March, but we've got some big plans coming, and especially with iOS 9 coming out, we're waiting to update that to see what we have to fix for iOS 9. Every time there's a new operating system release, inevitably there's some fixes you have to make to your app. But again, it's been very well received on users. These are unsolicited reviews and ratings, 4.5 out of 5 stars, 157 ratings. Not bad, I think. That's just the US as well. So what we featured in this is kind of like what you saw earlier in that old historic Himmelblau app, but we've done it in a little more colorful and visually interactive environment. So we have properties for over 1,000 compounds. So we'll show some screenshots of these in a moment, but an overview of the features. Properties for over 1,000 compounds, that's things like molecular weight, boiling point, CAS number, enthalpies of vaporization, etc. Of course, the unit converter, and this is important. The unit converter, we've got over 40 different types of unit converters in there. We'll talk a little bit about the most popular ones a little bit later. But what we've done with the unit converter is we've actually leveraged that so that I can solve equations such as ideal gas law, Pang-Robinson, heat capacities in any units I want. So I have one form of the function, but I can then do conversions in code and get answers in any units that are convenient to me. We have steam tables built in, so for water, but also some common other substances, R134A, ammonia, air. We're working on expanding that quite a bit in the next release. Of course, equations of state, and then those functions that we really need in mass and energy balances, like the Antoine equation, heat capacity, pressure head, and then delivery of reference materials as PDFs. There's also a built-in calculator, which you might be seeing as one of the icons there, and just a whole bunch of other small features. So to take an example, screenshots of what goes on the iPhone version, here I've got a compound, and I've just picked methanol, but again, there's over 1,000. Some are very common, some are not, and we'll talk a little bit about the most popular substances a little bit later. But of course, I get some information on the molecule. I get the formula, CAS number, physical properties. One thing we've also leveraged with the compounds is that there's a lot more information, obviously, out there that we can access. So instead of trying to pull it all into the app, we've just created a link to the Wikipedia page for any substance that exists on Wikipedia, and we can go right to methanol, right? So the user can click that, get a view, some more information on methanol, maybe some historical information, synthesis information. So we don't have to put everything in the app. We can leverage on existing resources like Wikipedia, which I think is actually very solid nowadays for this sort of chemical information. Okay, so another screenshot you're seeing on the far right is the Antoine equation. Here, obviously, Antoine equations in Felder and Rousseau were taught that the function is log 10 of P star, millimeters of mercury, some function of Celsius. Well, if I don't want to solve it in that form, let's say my problem requires me to solve it in atmospheres and Fahrenheit, we can actually do these conversions within the app. So if you were to touch the button there that says ATM or degrees F, you'd actually bring up a menu that lets you choose your pressure from 10 or 20 different types of pressure units. And then, of course, if I click on Fahrenheit, then I get a bunch of different temperature units as well. And I'll solve that equation in the form that I need it to be solved for, rather than always in millimeters of mercury and Celsius. So some more iPhone screenshots. We'll have this screen and one more. We'll just talk you through briefly. The unit converter, pressure on the left, right? So there are all my common pressure units. There's a bunch more that you can't see. And the user can just tap any of those cells and input the value, and the values of all the other cells will be returned. So if I tap millimeters of mercury and type in 760, then I'll get 1 ATM, 1.01, 325 bars, et cetera, et cetera. And we've got over about 40 different types of unit converters, pressure, temperature, volume, et cetera, et cetera, et cetera. The next thing, the center screenshot here is the steam module. So again, so instead of doing double interpolations or single interpolations on saturated steam, what we do then is we just enter a temperature or a pressure in whichever unit that we're interested in, Kelvin or atmospheres in this case. And so again, type in 298 Kelvin and we get the corresponding saturation pressure in atmospheres, but we also get all those physical and transport properties that are shown below. If I do that for superheated steam, then I'd put in 2 inputs and get the properties. And there's some, obviously one of the things that comes up is, you know, we can enter in wrong values. So the app is actually very intelligent and warns the user and prevents calculations from running. Let's say if they enter 0 Kelvin, that's just not going to work, or 7,000 Kelvin, we're probably going to have that calculation shut down either. So there is some information also given on the acceptable ranges of inputs. Okay, so then finally, talking about on the right here, we've got a dimensionless group, and of course we know how tedious these are to calculate when I have a mixed bag of units. So there, purposely, I picked a bunch of units that don't translate to a dimensionless group when they're taken alone, right? Centimeters, meters per second, grams per centimeter, and centipoise. If I put those values together, I certainly will get the wrong value because those units don't cancel. But what we've done then is we've internally pushed those units to be the same such that we get a dimensionless unit. So it's more convenient to run Reynolds numbers calculations with the units I have rather than doing conversions ahead of time and getting the appropriate answer at the bottom. And if you wanted to check that, you certainly could put in units that cancel, you'd get the same result. But again, this is one of those things where we're streamlining tedious calculations that simply involve unit conversions. And of course, I still believe students need to know how to do their unit conversions, but at the same time, we need to be practical in how we go about our work, and is it worth our time to do all these unit conversions ourselves. All right, so one more set of iPhone screenshots, then we'll move on to the iPad. Same concept here in Peng Robinson. Here I've got a substance that doesn't show the name, it should have. But again, I've picked my pressure and my temperature. I calculate a specific volume out of that in liters per mole. I also get all the relevant Peng Robinson constants there as well. Those are automatically calculated based on the substance properties. In the middle here is a little calculator that I wrote recently. I think this is pretty interesting because it operates more like a MATLAB interface than other calculators you're going to find on the App Store. And that's been very well received. I think it's very convenient. Obviously, you can see I can define variables with this. I'm not aware of other calculators for iOS that do such a thing. We have very simple graphing calculators. We've got other calculators, but this kind of MATLAB-style calculator is the first that I know of on iOS, so we're pretty proud of that. And then finally on the right, I mentioned we can deliver reference materials as PDFs. There's a Mollier diagram for steam that we've made. So I actually had my student, David Revita. He probably thought it was very tedious at the time, but I wanted to demonstrate how nice we can make these kind of charts look on iOS, right? If I was to go into a textbook, I would see that Mollier diagram, and I'd see it in black and white, and I wouldn't be able to scroll and zoom in. So this is not only a prettier Mollier diagram than what we probably find in a book, but I can also zoom in on it. So through the swipe gestures and the pinch and expand things that are accessible on iOS, I actually can get a very close-up look at that diagram and dial in to getting data that I want. So again, just another nice feature of something I can do just on a phone with delivering reference materials. It doesn't all have to be code and fancy things. There's some real value, I think, in just delivering full-color graphs that normally are relegated to the backs of textbooks. So then to move on to the iPad version, we call this one HD. This came out a few months later for the iPad, May 2012. We started again. It's specifically designed for the iPad. It has features that you won't see in the iPhone. Even though both versions are updated simultaneously now, that's by design, they're not the same. So again, on the iPad version, we see everything that we had in the iPhone, but we've incorporated things like graphing. And so I'll show some examples of that coming up, which is very powerful. We have some VLE calculations, Raoult's law, and Wilson model for certain substances, Newtonian fluids, matrix calculations, some spreadsheets. Obviously, this isn't as powerful as Excel, but it gets the job done in some cases. We also have a calculator, a graphing calculator. We have some things I call Chemi tools, which I'll highlight a few of, practice problems, which are randomly generated, save your work, and integration with email, Twitter, and Facebook. So here's one of the first examples. So I showed you earlier we have on the iPhone we can run calculations, but on the iPad not only can we run the calculations, we can also show the graph. And that graph is also exportable, so I can send that to myself, I can put it in a report. So again, very powerful. I can calculate in whatever temperature I need, I can return the delta H or the heat capacity in whichever units I need. I can make this graph, which is also fully labeled for me. I've got the legends, I've got the relevant information. And again, I wanted to do the graphing alongside because one, I think it's powerful to show what this function is doing. We see a polynomial of third order, more or less. And again, students don't always appreciate what that means. And to visualize such a polynomial in one's head may not be easy, right? But here, I'm not only graphing the function, I'm calculating it, alongside, and I can use that graph and export it. Here we have a Wilson Model Txy diagram for carbon tetrachloride and acetonitrile. That's fully generated based on Wilson Model parameters, which are built into the app. Again, I can export that graph. I can actually export the underlying data as well if I want to make my own graph in Excel or do something like an XY diagram to make McCabe-Thiele diagrams. I can certainly do that. And again, it's got some interesting features that go with it. I can interpolate, right? So I can plug in an X value, get the temperature, get a corresponding Y value. So again, this has made my life easier when it comes to designing problems for my separations course. Of course, we talk about TXY, PXY diagrams and mass and energy balances, but we don't truly use them, I feel, until separations. And so this has made my life a lot easier. And we're going to expand this into hopefully a full-on McCabe-Thiele module not far down the road. One of the other things I found was quite tedious in mass and energy balances was solving combustion equations for hydrocarbon fuels especially. Now, they're all the same approach, but here it's a lot faster. So one of the things I found was these equations take a long time to balance. When I'm doing combustion of the fuel, we get our theoretical oxygen, we run combustion conditions, we calculate inlet compositions, and if you scroll down, you can actually press a button which burns the fuel and gives you the outlet composition. So again, this is one of those things that, sure, the students can benefit from it, but it also benefited me in terms of how much time it saved me designing problems like this to put on exams. And I could rely on the fact that once I knew the code was working, anything I threw at this would work fine, and I could rely on the answer. So again, this is an example of maybe something I built for myself first as a matter of convenience, and then it has applicability for students as well. We also have some interesting approaches to fluids. So here's an example of a tank filling module where we have a spherical tank of a certain radius and volume, and we're interested in figuring out if it was what the liquid height versus the liquid volume, right? So here we have a graph of a spherical tank, and we show height versus volume, and we can solve this any number of ways. We can calculate the fill parameters based on percentage full, the liquid volume, or the liquid height, and we can use any units, of course. That's all still built in. Another fun thing that's powerful on iPad is I can click that little I button that's shown there, and I can bring up the actual equations and parameters for this type of tank. So not only am I calculating it, but I also reinforce the underlying equations and information that go with this. So again, I get to put layers of information on my module here. So it's not just about solving the equation, I can also show the fundamental underlying math. We also have a linear equation solver. Again, I don't know of many, if any other of these on iOS systems. So again, instead of having to go into other software, we can intelligently write in equations here that are parsed automatically for us with a certain framework I'll talk about later. You can see up top, it's identified the variables as x1, x2, and x3. I've put together an input matrix that you can see down on the lower left, and it throws back a solution to me. And all of that happens automatically. If the equation is solvable or the system of equations is solvable, it returns a solution. Here is something I'm actually excited about, and I wish we had been able to spend more time on these so far, and this is the concept of these practice problems, which are randomly generated ad infinitum, right? So I can infinitely generate this problem in any number of different ways. And this is just a simple mixing tank as an example where I have two streams coming in, a stream coming out. I write the code to specify the variables that are in black. So the student or the user is given two mass fractions of one component, and they're left to solve the rest of the problem. And you can see here that the correct answers are highlighted in blue, and this is automatically checked. So I had to put those answers in myself, click Submit Answer, and it tells me whether I'm right or wrong. You can also see here on the left, I have a calculator that I can bring up simultaneously, so I can be doing work on the left, solving those variables for those variables in the app. I don't have to do this by hand on a piece of paper. I actually can solve right next to it, drop in the variables into their appropriate stream or mass fractions, and I'm good to go. So I don't have to incorporate paper to do this. I can actually solve it if I know what I'm doing on the calculator there on the left. We also have some nice reference PDFs. I'm just highlighting here a psychrometric chart. Again, these are one of those charts that nobody seems to like, but I thought, well, maybe if it was in color, it'd be a little bit more friendly. There's obviously a lot going on, but again, this is a psychrometric chart. It's simplified, meaning it's derived with some assumptions, but nonetheless, I can scroll and zoom on this, and again, I think it's just a little bit more exciting to look at, a little bit nicer than the psychrometric charts we'll find at the back of most textbooks. Also, here's the fanning friction factor diagram. Again, probably never seen it in such color. So again, it's just taking a diagram that we find in a lot of textbooks that's derived from mathematical equations and then just regenerating it to be something visually attractive to look at. And again, I can interact with it. I can export this. I can mail this to myself and print it if I want to. So that's another thing that we've emphasized is not only does the app give you data or give you access to data, you can also get that data out of the app itself. So again, the response to these apps has been overwhelmingly enthusiastic. Students really didn't consider that iPhones and iPads would have use in education. Maybe some of the newer students are getting more used to iPads, and they've grown up with it in their elementary schools and high schools, but a lot of the students the past couple of years really were new to this just like anybody else. And they weren't thinking of this as terms of education. They were viewing it as entertainment and communications, right? So Facebook, Twitter, Instagram, Netflix, some games maybe. But they hadn't thought that I can use my phone to do chemical engineering work or help me in my chemistry classes or my math classes for that matter. They liked the accessibility of the spreadsheet and the matrix tools that we provided. Students may say that they're good at Excel. A lot of my students claim to be good at Excel when they start, and then they quickly realize that there's a whole lot more to it than just entering data. And MATLAB is certainly another intimidating tool for a lot of students. So the app kind of is a bridge to those more powerful software platforms, I think, as well. And they like being able to see advanced concepts in mass and energy balances before they get to fluids, thermo, separations, et cetera. So this actually kind of gives them a taste or, you know, an idea of what's coming next, and they can start to think about these concepts ahead of time. Okay, went the wrong way there, sorry. So again, challenges and opportunities that I've identified. Of course, not all students have iPhones or iPads, but can we require an iPad in the Chemie curriculum? This is something I've certainly kicked around here at Alabama. Some would cite cost as a barrier because these devices cost $400 or more, but the iPad mini and the used device market, which is actually probably quite big now, I can get a used device at a lower price, lowers that barrier, right? I can get those for less than $300. And when I consider the cost of purchasing a new textbook, it can be over $200 for each textbook. And even if I rent a textbook or sell it back, again, that's going to add up to students over time. So the cost of buying a powerful iPad-type device really isn't all that bad when we consider the cost of textbooks and everything else students have to pay for. Now, I ask myself a lot, how user-friendly should apps be, right? Do we somehow circumvent the learning process by not allowing students to make mistakes, right? If I always correct them when they put in a mass fraction greater than 1, does that teach them, or should we allow them to fail? And that's something I'm still debating, is how user-friendly does the app need to be? Because there is some value in making mistakes, I believe. But on the other side, if I'm writing an app that's also going to be used by professionals, surely they're not wanting to make mistakes. So we have to kind of think about the level of the friendliness for the apps. And again, the apps so far have been great for well-defined equations, but the idea is to make it more open-ended. And again, I see that as parametric analysis in mass and energy balance courses, as well as perhaps some process simulation modules. So benefits that I found to teaching, the mobile approach is saving me time without a doubt. Things I talked about earlier, much more rapid solving of equations, accessing data, writing homework problems. Students really like the visuals. It's much more engaging when I have my lecture notes on one projector and I'm showing the app on a projector alongside of it They really like to see the graphs alongside the equations, the shapes of the molecules, different features that don't go in a traditional course. And again, I think that appeals to different learning styles. I was certainly a student who was good at math, but as mathematical equations got more complicated, I kind of zoned out. But had I been able to see a graph of what a Bessel function was doing or something like that, that would have appealed to me a lot more. So I can relate to that. And then obviously, we can enhance content in mass and energy balances, as I mentioned. Okay, so what I want to talk next about briefly is a little bit about the insights into the actual usage of the app. So one thing that we did early on was import the Google Analytics SDK framework, which runs within the app. It gives us a lot of information on what user interaction is occurring, but it's all anonymous. We don't know who these people are. We just know what city they're in, perhaps. And I can get that framework for anyone who's interested in that. If you're an app developer or a student considering developing apps, there's a link there to get that Google Analytics framework for iOS. And again, this is a powerful way to gain insight into what modules are and aren't being used. As we found, we've written some really cool modules, I think, but when you code it, they don't always actually use it. So again, Google Analytics tells me that, so we're not putting a lot of effort into things that aren't necessarily going to be as useful to the users. And I can visualize the usage worldwide at country levels, state levels, even city levels, and there's been some unexpected and surprising results, which I'll go over now, as far as where the app is being used, and then we'll talk about how it's being used. So again, we truly have had a global impact, and this wasn't something we could envision when we started. So since we released version 2.0 on May 15th, 2013, we started tracking app usage. And we've seen the app launched in over 49,000 devices, over 320,000 times, in over 177 countries. And to date, it's facilitated over 875,000 calculations. So this was not, this has exceeded our expectations wildly. But I still think we're just getting started. So as would be expected, the U.S. is the #1 country of use. We probably have the most iPhones and iPads. But our next 7 countries are kind of surprising. We see Mexico accounting for 1/7 of our users, then Thailand, then Colombia, and then finally at the UK at 3%, 2.8%, we see our first country in Western Europe, followed by Guatemala, Canada, and Brazil. So we've seen really then some intense use in developing countries, and in Mexico especially, this is really something that I didn't expect. So when I map the global chemi activity, and this is where it's interesting, the data we're generating from the app, I wonder then if it's not also simultaneously generating a map of global chemical engineering hotspots. And this wasn't the intended purpose, but again, this is not, you don't always, you get more than you intended sometimes. So when we look at this here, I've labeled some cities, right? So the #1 city for app usage is Mexico City. I've never been to Mexico City. I'm fairly certain I don't know anyone in Mexico City. We haven't marketed this in Mexico. But nonetheless, we see huge adoption in Mexico City. #2 is Tuscaloosa, but I call that the Alabama effect because I'm here, so our students are hearing about this the most. Then we look around the world, then we have Bangkok, Houston, #4, okay, traditional chemical engineering stronghold there in Houston. #5, Bogota. 6 then is also Monterrey, Mexico. So we have big use in Monterrey, Mexico as well. Guatemala City, 7. Back to Dallas, 8, another chemical engineering region. Texas, maybe not unexpected. Oxford, UK should be 9. I believe, I think I have that labeled wrong. And 10 is Atlanta. So that rounds out the top 10. But I've also put in some other interesting cities around the world. Obviously, that's not all 50, but nonetheless, we've got a good number of users scattered throughout the entire world. Also, ignore that big dot that's in the center of the map at 0, 0. If it can't log data for whatever reason, it gets assigned right there. So we don't have a huge number of users off the coast of Africa. That's just users that, for whatever reason, we didn't get the data from them. So within the U.S., I was also surprised. Again, maybe not so much by Tuscaloosa being #1. Again, that's just the effect of me being here. #2 is Houston. It makes a lot of sense. But #3 was Oxford, Mississippi. Again, they love us at Ole Miss. I haven't been to Ole Miss. I only know one professor there. But if there's anyone from Ole Miss listening, thank you. Appreciate it. And then obviously we go around the country. We see some very big cities where we have a lot of use. Dallas, Atlanta, Chicago.
But then we also see Minneapolis, of course, 7, Nashville, 8. But then we start to see some use in some really smaller cities too. So number 14 really surprised me, Angola, Indiana. I had to look up what was there, why we got so much use out of Angola, Indiana. So that was actually Trine University. So again, I want to say thanks if anyone from Trine is listening. I appreciate all the use you're putting into the app. And then again, we might expect, again, some very big cities, Philadelphia, New York, Seattle, Denver. Also Colorado School of Mines coming in at 15, obviously, with all that use in Golden. So again, it's a mix here of really big cities, which we'd expect, but also university towns as well. And so it says to me, we haven't quite gotten into many universities just yet. Again, I'm not even seeing my alma maters of VCU and Boulder logging quite these number of sessions. So we have a way to go. So let's briefly talk about what features are most popular. Again, this is important. I think it also tells us about not only what students need to know, but what we're teaching and what we emphasize and what they're working on. Obviously, unit converters account for the vast number of use of the app. Probably at least half of the app is based on unit converters. Well, maybe not quite half, a third. Reference materials, steam, obviously quite important. Then we have chemical compounds, Antoine equations. Then we see it kind of drop off pretty rapidly. Ideal gas, other equations of state. And then this interest in R134A, I suppose perhaps there's maybe some mechanical engineers that are picking this up as well. The most used unit converters, this is really interesting. Even though we've coded 40 unit converter modules into the app, about 10% account for 90% of use. And they're the ones you might suspect: pressure, length, temperature, volume, mass, energy, density, area, and then volumetric flow rate and dynamic viscosity. So that says actually the average user is using the converters to do some very expected unit conversions, right? There's nothing particularly outside of the box here. So these are the ones you might expect. So it's just interesting to see how much they're used in proportion to all the other 30 unit converter modules that we put in the app. Again, it goes back to if you code it, it doesn't mean they'll actually use it. Also, the top 20 most viewed chemicals this year, I think this is interesting. It reads almost exactly as you might expect. It's like the top 20 of all commodity chemicals for the most part, minus sulfuric acid, which I think was 21. But yeah, this is the laundry list of chemicals you might expect, especially in a mass energy balance course. Water, benzene, air, ethanol, methanol, CO2, methane, etc. I mean, this is a list of commodity chemicals. So again, not surprising, but out of 1,000 chemicals in the app, again, this is probably, again, 80 to 90% of all the use. So it says there's a very small subset of substances that users are most interested in. And so again, maybe that's something to emphasize going forward. Current plans, so again, expanding the app. Again, I think there's major opportunities to especially build a user base among students. The exposure is limited, but I think growth is accelerating. We actively listen to what our users need, or if they find bugs. There's a couple ways to reach us on Twitter. Vector254 is the company that John McLemore and I founded, which markets the apps. You can find the apps on Facebook at ChemiApp. And again, some of the things we want to do is expand the thermophysical properties based on some of the analysis I showed on the earlier slide. Users would like to add custom compounds. I see that really is value to industry, where there's specific substances that may not be in the app that are needed. Again, we want to really expand those practice problems and hopefully design a full course of study in mass energy balances and eventually thermo and separations. And then inevitably, we're going to have to keep that app updated for to be compatible with Apple's new operating system that's coming out any day. So briefly, I'll also talk about our numerical solver, which I call ODEsseus. It's a play on Odysseus from Homer's Iliad and Odyssey. So it just kind of dawned on me one day. I'm going to call my app ODEsseus. So we've actually written a Runge-Kutta-based numerical equation solver. If you've worked with polymath, then certainly the workflow of this is going to feel familiar to you. But again, there was no real differential equation solver we saw for the iPad. So this was a real opportunity. Here I've got a system of chemical reactions that depend on each other. I can run the system. I can specify constants, initial values, final values, temperature, just as we might expect. we can run those Runge-Kutta calculations quite easily, and we'll generate our graphs on the fly. They look very pretty. That's intended. We want nice-looking graphs. We can then switch over to the graphing module. We can take that data. We can change the colors. We can change the legend, the axis ranges, whatever we might want. We can save the data as a CSV. We can also save the graph as an image file. So all of this is exportable. I can send that graph to myself or whoever and streamline my workflow. We can also look at the data individually based on the Runge-Kutta solving method. Can interpolate in between values, so if the value that I need isn't specifically there, we have a module that linearly interpolates and finds us the value that we need and the corresponding values of the other variables. So again, ODEsseus always is a work in progress. I think it's still quite powerful for what it can do now. It's nowhere near complete, but I think it's been going quite well. And again, stay tuned for more on that in the future. So again, I want to talk a little bit then if there's any students listening or AICHE advisors listening or just anyone who's interested in general in some app design. We are hosting a student mobile app competition. This is the 3rd year. This was started by Robert Heskett from Rowan. Scott Fogler is involved. I'm on the committee as well. And this is open to undergraduate student teams. The qualification is that at least half the team must be AICHE members. Students are certainly welcome to bring in computer science students or electrical engineering or whatever it might be, but to be eligible for an award, they have to be at least half AICHE members. The best overall app will get $500. The best app focused on safety will also get awarded $500. The code, the IP remains with the students. The committee will certainly evaluate the code and wants to take a look at it, but the students own the app. By submitting it, they're not transferring anything over to AICHE. The submission deadline is obviously approaching pretty soon, so we'll get to look at which chapters have done it. But again, maybe this is just good information for anyone interested next year as well. The student teams will present a poster and demonstrate their app at AICHE in Salt Lake City in November. And there's a link to more information there at the bottom. So for anyone interested in iOS app development, I'm going to do a brief overview of this. I know some of the people would be interested in it. So iOS and macOS apps are typically coded in Objective-C. We can also pull in code from C and C++, which is great. The primary interface for building Mac or iOS apps is XCode, which I can only get through the App Store on a Mac computer. So there's no PC equivalent to do this that I know of. And again, I must register for an Apple developer account to distribute and sell apps, and that costs $99 a year. You have to go through Apple's review process before you can put your app out there, and there's some other additional benefits you get from membership. So coding in XCode, this is the interface. It's basically a file organizer / coding, debugging, simulator. It's got a whole bunch of modules here, so again, this is just a general screenshot of one of the codes for the app. Again, we just define methods and variables and everything like we might in any other coding interface. So that's overview of XCode. The coding side, XCode also has a storyboard side, which is where I graphically design these interfaces. So everything you saw on the previous slides is laid out on what's called a storyboard in XCode, and I provide connectivity, and that's where all the actual graphical interface happens. When I'm ready to upload an app, when I've checked it, I know it's ready, it's something I want to show the world or sell, then I'm going to go through iTunes Connect, and that's where I also have to upload screenshots. I can put a video in, even nowadays, put in your keywords, set your pricing, etc. So again, once I'm happy with that, I'll go through iTunes Connect. For anyone interested, again, there's so many resources out there for coding, tutorials, and help. A place to start for me back a few years ago was just to get a book. Amazon has plenty of good options. I won't specifically name any. There's a lot of good options here, especially for iOS that range from basic to advanced topics. XCode has a lot of built-in help, as we might expect from a coding environment. Lots of inline help, templates for functions, identification of errors, possible remedies. StackOverflow.com is one of my go-to resources, if not the go-to resource. Free and openly accessible message boards for coding Q&A. So if I want to just know whatever, how to transform a string into a double precision variable, I can do that. If I don't know what I'm doing, I can go to Stack Overflow and do a quick search and find it. There's also some nice websites that teach text and video tutorials on all levels of coding topics. So again, lots of resources. The other thing that maybe isn't apparent is we don't write all the code ourselves in the Chemi app, and no one does. And nobody nowadays is writing all of their code themselves. So there's basically a repository framework called GitHub where we can get free and powerful frameworks to power our apps. You don't need an account, but if you register for an account, which is free, there's some benefits that go with that. So anyone listening who might be interested in writing code, especially students for science and engineering, DD Math Parser is great. That's running the back end of ODEsseus. It's turning text strings into equations. CSV Parser also has been useful to pull in CSV files, which then I can turn into app data. And all those pretty plots and graphs you saw earlier are through a framework called Core Plot. So again, we make heavy use of that. And then some other frameworks that are useful for managing user interaction. MK Store Kit, that's going to manage your in-app purchases very easily for you if you want to sell content through the app. App iRater, I know that looks like App Pirater, it's App iRater, is that module that you always get. You see it says remind, won't you rate our app please? That's all App iRater, that's great. App reviews are very valuable to you when you're putting apps on the App Store. And then another one that's been useful is Dropbox Uploader, where I can send files to a user's Dropbox. Finally, just some quick information about our apps, where to find them. All these apps can be found on the App Store, marketed under Vector254 LLC. Again, that's the small company we started to basically hold these apps for us. We found it easier to work with Apple through the App Store as an LLC rather than as an individual. Again, you can purchase the Chemi AppSuite and ODEsseus together as a bundle for $2.99, which is a discount. And if you're just interested in the engineering unit converter, that's a free app with some premium content that can be unlocked later for 99 cents. Anyone who's going to be attending AICHE, I'd encourage you to come to the session on apps and chemical engineering, session 10, on Sunday, November 8th from 4 to 5:40. I know that's the first day of the conference, but make it out if you can. Salt Palace Convention Center, 250F. There's the link to the session for you. The student mobile app competition is going to be held on November 9th during the poster session, and then the finalists will be expected to give a brief oral presentation to the general audience. So with that, I want to thank everyone for listening, thank John and the CAST division for inviting me to do this webinar. It was a lot of fun topic I'm really passionate about, and I hope I've got you all excited as well. So any questions, I'll be glad to stick around.
Fantastic, Jason. Well, thank you so much. We'll go ahead and start the question phase. If you have a question, feel free to put it into the chat window or unmute your microphone and ask away. So we have time for about maybe two questions or so. So, Jason, let me just go ahead and start with one. So I know you mentioned, like quizzes and kind of trying to gauge their understanding, use it as a teaching tool in the classroom. I've used AICHE Concept Warehouse quite a bit. I imagine like there's probably an opportunity to do like a built-in quiz, be able to test the students, be able to see their feedback right away. Do you have any thoughts on that? How can you incorporate this type of quiz generation into the classroom, get feedback during the class?
Yeah, no, that's a great question, John. I mean, one of the things, of course, we'll assume everyone has the device to run it on. And yeah, I think what you could do is you could actually have them, we can code a module with a quiz, which isn't really far off from what we have. And what they would do is they would fill out that quiz. It could be graded automatically, and then they'd be expected, it'd be trivial to click a button and send me a PDF of everyone's files or quizzes. So that's really not that far off. It's just a matter of getting these in everyone's hands and being, basically shifting to that mode, right? So if everyone had that, it'd be no problem really to either borrow the AICHE concept questions or work with them, code those type of questions into the app, get all the students on it. You could probably even say, you have the next 10, 15 minutes to do this, complete it. It would be graded automatically because the engine behind the code would grade it, and then they just click send, and I'd get a collection of PDFs. I think that's not far off.
Great. Okay, we have a question from Christian. He says, I might ask, there's definitely value to understanding the underlying principles being calculated in the app. At the same time, you don't want students using a black box. At what point do you introduce the app in a student's curriculum?
Yeah, that's great. What I've done in math and energy balances is I've run through these examples by hand first. So I always do the hand calculations first, and I just after I show them the underlying principles, then I say, okay, we just did that mass fraction to mole fraction conversion. You saw how much work that took, and so if you appreciate what just happened, and you're going to believe that my code gives you the same answers, right? So I always have them solve it by hand, and then I show them that the code generates the same result. So I never put the app first when I bring in a concept. I always bring it in after. I make sure that we've at least run through the calculations once or twice, and then say, okay, now that you understand it, or you tell me that you understand it, now we'll do it in the streamlined way through the app.
Fantastic. Okay, and we have a question from Bruce. Where do you get the data permissions?
That's a great question, but the point is the data permissions from things like these physical properties, I've done research on copyright, and these types of physical properties are not something you need permission for. Essentially, data of, boiling point, melting point, cast numbers, these types of things are open, right? This isn't necessarily data that anyone owns, and I think that's a common misconception, but these data are representations of physical properties, which isn't something that can be copyrighted or patented.
Great. Okay, just want to read one of the customer reviews on the Apple iTunes website. As a scientist, I use units, chemicals, and equations every day. This app has surprised me every day with something it has that I didn't know about. This app makes it easy for me to do quick unit conversions, learn chemistry, and review science. I love this app and would highly recommend it to anyone who lives on the planet Earth or anywhere in the universe. So I'm thinking about, when it couldn't find the location, maybe, I don't know, who knows where those are coming from. But, he definitely recommended it to everybody in the universe. So.
Yeah, I didn't write that one myself.
Okay. So just a follow-up question from Bruce.
Yeah, even direct. Yeah, I'm seeing those now. Yeah, go ahead.
So just a question about derived constants, equations of state, other thermophysical properties that might be part of databases. At what point can you pull those in from these extensive? Because I think what you've shown is fantastic there.
Yeah.
And, for pure compounds especially, there may be a whole other database of mixtures, mixture coefficients, other things. At what point are you going to start using maybe from these databases where you might have to license some of the data?
Yeah, so one of the, right, and that's true. I mean, there's probably some points where you would need to license a wholesale database. One of the frameworks that's openly available is something called CoolProp, which is an open source, publicly available. It's very similar to RefProp, but I mean, you can go online and certainly find CoolProp, and that's one of the things that we're having run steam tables and other state properties. So again, there's a lot more open access chemical information out there than we might believe there is. But yeah, I mean, we're certainly not using a wholesale database, but also there's plenty. I mean, I think just go online now. There's plenty of information out there as far as physical properties, and I mean, a derived constant. I'm not sure what Bruce is referring to there as far as particulars, but there's a lot more information on the web for chemicals that anyone can access than there is in this app. So it's not all so secret, I think, anymore.
Fantastic. One more question. I think this will be the last one. What is your opinion about using the app versus teaching important skills related to software use? For example, Excel and MATLAB, which are used extensively in industry and academia.
I think it's a gateway. I don't think you don't get rid of Excel and MATLAB. I just think the app or apps in general can be a gateway to those more powerful softwares. We're not out to recreate Excel and MATLAB by any means, but I think when you throw those at students, sometimes they're not comfortable and they're intimidated by it. So again, it's kind of the first step towards getting them there. And again, I agree, Excel and MATLAB are invaluable to professional engineering work, and there's no intention of replacing them.
Fantastic. Well, excellent presentation, Jason, and appreciate the insights and comments. I guess we have just one, somebody tried to sneak in a question. Do you also know if there are industrial users of this app?
I believe so. I mean, if you go through the reviews on the App Store, there's certainly reviewers who make reference to their use of this in industry. And through students that go off and do co-ops, I know they've also gotten good feedback from their supervisors who are not students, obviously. And yeah, it's not been, as far as I know, adopted by one company and used extensively within a company, but we've certainly got feedback from industrial users, and they're pretty happy with it.
Okay, well, fantastic. Well, thanks again, Jason. Thanks, everybody, for joining this webinar. I'll go ahead and end the recording now, but I'll post this content on YouTube so that you can access it later, maybe from your smartphone. So thanks, everybody, for joining, and thanks, Jason, again, for the excellent presentation.
Thank you, John.